In this class, we will discuss the chi-square test and the chi-square distribution, which is used to test hypotheses concerning correlation between variables measured using nominal or sometimes ordinal scales of measure. In the last class, we discussed hypotheses involving correlations between variables measured using interval or ratio scales of measure. Well, this is a very common way we correlate variables. At times, we are faced with variables using less sophisticated scales of measure. However, we are also interested in how these variables correlate. For example, is there a relationship between obesity, measured yes or no, and cardiovascular disease, measured yes or no? Similarly, is there a correlation between locus of control, measured internal or external, and whether or not someone has ever received a diagnosis of depression, yes or no? In these cases, the variables under consideration are measured as present or absent, yes or no, or individuals are categorized in some way, say as obese or not, or as suffering from cardiovascular disease or not. So the issue is, can we predict someone's group membership in one variable based upon their group membership in another variable? The chi-square distribution and some of the chi-square tests will allow us to explore hypotheses involving variables measured using nominal and sometimes ordinal, but mostly nominal scales of measure. Well, the first place to start is to describe the chi-square distribution, and as we discuss it, you'll want to look at figure 13.1 on page 299 of the 8th edition of the Spats text. Like the F distribution, the chi-square distribution is positively skewed and becomes more symmetrical as degrees of freedom increase. And just like the F distribution, because the chi-square test statistic is based on squared values, there are no negative values, and the range of the chi-square distribution is from 0 to positive infinity. In addition, because there are no negative values, the chi-square test is a non-directional test with no ability to evaluate a two-tailed hypothesis. Also, like the T and the F, the chi-square distribution changes shape as degrees of freedom change. Before going to the next slide, see if you can answer this question. What happens to the critical value of the chi-square distribution as degrees of freedom increases? The answer is that unlike the T and the F distribution, the critical value in the chi-square distribution increases as degrees of freedom increase. If you look at the chi-square table in the appendices, when alpha is 0.05, you'll notice that at 1 degree of freedom, the critical value is 3.84, and at 2 degrees of freedom, the critical value is 5.99, and the critical value keeps increasing as degrees of freedom increase. So let's learn about a chi-square distribution by creating an example. Let's say we speculate that one's attitude towards Governor Schwarzenegger of California as a politician or as a governor is related to one's attitude towards him as an actor. We might hypothesize that those who like his films have favorable attitudes towards him as a governor, and those who don't like him as an actor tend to have unfavorable attitudes about him as governor. So let's say we randomly sample 100 individuals from the San Francisco phone book and ask them two things. Ask if they like his performance as an actor, yes or no, and if they like his performance as a governor, yes or no. Which is to say, we are measuring both variables with a nominal scale. If you'll recall from an earlier class in descriptive statistics, neither a mean or a median can be meaningfully computed for a variable using a nominal scale of measure. So as a result, we will address questions concerning correlation with variables using nominal scales by evaluating the frequency distributions of the variables. So instead of considering means or correlation coefficients, we'll consider frequencies, or what some people call counts. The primary way we display the frequency data in a chi-square problem is in what we call a contingency table. And let's assume this is the result of our interview with 100 participants drawn at random. So what you see in this slide is a contingency table. This is a 2x2 contingency table, meaning the first variable has 2 levels and the second variable has 2 levels. If we modified our question about his performance as governor by allowing individuals to respond yes, no, or neutral, we would present the data in a 2x3 design, in which the second variable, the attitude toward his performance as governor, had 3 levels. Notice that observed frequencies are presented in each cell, and we can see that 46 individuals said they liked him both as an actor and a governor. Also notice that sums of frequencies for each level of each variable are presented in the margins outside the table. So the sum of people who liked Arnold as an actor is 46 plus 22, or 68 individuals, or participants in our study. Our research hypothesis is that there is a correlation or relationship between one's attitude towards Arnold as a governor and their attitude towards him as an actor. Or to state the hypothesis as it is written in the slide that you have here, the proportion of responses into levels of the 2 variables are not equal in the population. Thus, we are saying that the proportion of yes-no responses for one variable are related to the proportion of yes-no responses for the other variable. Also here, please note that because chi-square is based on squared values and is a non-directional test, we will not be dealing with positive or negative correlations or relationships. The null hypothesis then is that there is no correlation or relationship between variables in the population, or that the proportion of yes-no responses for one variable are independent of the yes-no responses for the other variable in the population. Degrees of freedom in chi-square, what we have here is called a test of independence, is based upon the number of levels of the variables, not on the number of participants. The formula is the number of columns minus 1 times the number of rows minus 1. When we have a 2x2 design, our degrees of freedom equal 1, or 2 minus 1 times 2 minus 1. If the study were expanded to be a 2x3 design, our degrees of freedom would be 2, or 2 minus 1 times 3 minus 1. The chi-square formula contrasts the frequencies we observe in each cell, the O, against the frequencies we would expect to observe if chance alone was operating, or if the null hypothesis was true. And that's what the E is. E is what we would expect. O is observation, E is expected. Thus, the numerator of the chi-square evaluates the effect of treatment by squaring the deviation of what we observe from what we would expect if the null hypothesis is true. Thus, the larger the gap between the observed and expected, the more likely the null hypothesis will be rejected. Consistent with all our other test statistics, a measure of sampling error or chance alone is what we see in the denominator of the chi-square statistic. So the treatment effect is divided by what we would expect by chance alone, or the expected value. So how do we determine what is expected by chance alone in each of the cells, or our expected value? The answer goes back to the multiplicative law of probability, which we learned in a previous class. So an expected value could be expressed as follows. what is the probability somebody would be in both column 1 and row 1? Or what is the probability someone would be in both column 1 and row 2? So let's try to answer this by first of all addressing what is the probability of being in row 1. Based on the data in the contingency table, the probability of being in row 1 is the number of total participants in row 1 divided by the total number of participants, or 68 divided by 100, or 0.68 is the probability of being in row 1. And based on the data in the contingency table, the probability of being in column 1 is the sum of the participants in column 1 divided by the number of participants, total number of participants, or 56 divided by 100 is equal to 0.56. Thus, the probability of being in row 1, column 1, is 0.68 times 0.56, the multiplicative law, which is equal to 0.38. When we multiply the probability, 0.38 times 100, we learn that we would have expected 38 participants to be in row 1, column 1 by chance alone. A formula that arrives at the same solution, that is more simple to compute, is as follows. The product of the row total times the column total divided by the grand total, or in the problem we just looked at, 68 times 56 divided by 100 is equal to 38. Before going to the next slide, see if you can compute the expected values for the other 3 cells of the contingency table. For row 1 and column 2, we would expect 68 times 44 divided by 100 equal to 29.92, or 30 participants. So we would expect 30 participants by chance alone. For row 2 and column 1, we would expect 32 by 56. Row total 32 times column total 56 divided by grand total 100, which is equal to 17.92, or 18. And for row 2, column 2, we would expect 32 by 44 divided by 100, which is equal to 14. So for row 1 and column 2, we would obtain a deviation of 8 once again, and a square, and once we square that is 64, which would be divided by 30, the expected value, which is equal to 2.13. For row 2 and column 1, we would obtain a deviation of 8 again, and then divide 64 by 18, which is 3.56. And finally, for row 2 and column 2, we would divide 64 by 14, which will equal 4.57. Finally, chi-square is computed by summing all of these values, or 1.68 plus 2.13 plus 3.56 plus 4.57. This all adds up to 11.94. So our test statistic is 11.94. Before going to the next slide, what would be the critical value for the hypothesis test? And would we accept or reject the null hypothesis? Because chi-square 11.94 exceeds the critical value of 3.84 when there is 1 degree of freedom, we would reject the null hypothesis. We would reject the null and conclude that the variables are related or correlated to each other in the population. We are not able to describe the direction of the relationship, so we couldn't say it's a positive or negative relationship, but we could inspect the contingency table to determine the pattern of the treatment effect. So going back to the table, we can see that we observed far more individuals than expected who liked Arnold both as an actor and governor, and we observed far more who disliked him in either role. So this is in the direction of the hypothesized relationship. We can also see that we received fewer ambivalent participants than expected, or fewer participants who liked him in one role but not in the other.